Okay, so today our focus is going to be on trying to figure out what f double prime determines about f. Now, once again, remember, just like the notes from yesterday, we use the first derivative to help us find characteristics about the original function. So now what we're going to do is we're going to say, okay, what does the second derivative tell me about the original function? And so before we do that, let's define what it is that the second derivative helps us figure out, and then we'll kind of know exactly what it is per case. So we could say if the graph of f lies above all of its tangents, on an interval I, then it is called concave upward on that interval. Okay, so basically what we're saying is if you draw out your tangents, and what you notice is if your tangents are below the curve, then that's suggesting that f is concave upward. So we'll draw a picture in a minute, and then you'll see exactly how it looks, and I'll kind of describe it in a different way as well. So this is kind of like the formal definition. So then what we could say is if the graph of f lies below all of its tangents on that interval, it is called concave downward on that interval. Okay, so as you could see, one way of describing it is if my tangents are above the curve. If they're above the curve, then it's the curve itself is concave downward. If the tangents are below the curve, then it's concave upward. So if I were to draw a curve, just a generic curve that looks something like this, what do I notice? So here, if you draw your tangents, notice how your tangents are above the curve. So from here to here, it's concave down. And then somewhere at some point, the tangents go below the curve, and that's concave upward. And then here, it's concave down. So the way I also think about it is, think of it as kind of like if you were to pour water in this, if the water slides down, that means it's concave down. If it holds the water up, it's concave up. So it's kind of like if it holds water, it's concave up. If you pour water on it and the water slides off, it's concave down. But if you think about it, by definition, I mean, the tangent lines in this case are below the curve. That's why it's concave up, and over here are above the curve. So I guess the question now is, now that we know how concave down and concave up looks, how could I tell if a function is concave up or if it's concave down? So just like the first derivative, how it helps me figure out when a function is increasing or decreasing, the second derivative is going to help me figure out when a function is concave up or concave down. So let me write out the concavity test. So the concavity test says the following. If f double prime of x is greater than 0 for all x in the interval I, then the graph of f is concave upward on I. So basically what this is doing is it's saying, look, if your second derivative is positive on some interval, then that means f itself is concave upward. Now remember, the second derivative is giving you information about f. And of course, if f double prime is negative, so if f double prime of x is less than 0 for all x in some interval, then the graph of f is concave downward on that interval. Okay, so once again, similar to the first derivative, the sign of the second derivative tells us about concavity. So if the second derivative is positive, it should look something like this. If the second derivative is negative, then your graph looks concave downward. Okay, so just by looking at this, we would be able to tell. Okay, so now moving on to our next definition, which is something called an inflection point. And an inflection point, just simply put, that's the point in which your graph changes from concave up to concave down. Okay, so what we could say is a point P on a curve y equals to f of x is called an inflection point if f is continuous there and the curve changes from concave upward to concave downward, or the opposite, or it could go from concave down or from concave downward to concave upward. Okay, so basically all we're saying is an inflection point is the point in which the function transitions from one type of concavity to the other. So it either goes from concave up to concave down or concave down to concave up. And so we could already see, if I were to ask you, how do I locate my inflection points? Well, that's where your second derivative is 0. But just like, remember how we said, just because the first derivative is 0, we're not guaranteed to have a local maximum in, but that's a potential local maximum in. Same thing goes with inflection points. Just because your second derivative is 0, we're not guaranteed that we have an inflection point there, but that's a potential inflection point. So can you think of that? So let's make a comment of this here. F double prime of x equals to 0 are potential inflection points. And so what I mean by this is I need to make sure that whatever, and at that x value, we need to make sure it changes from positive to negative. So for example, think of it this way. Consider f of x equals x to the fourth. See, what do I notice? F prime of x is 4x cubed. F double prime of x is 12x squared. And what do you notice? At x equals 0, my second derivative is 0. And so notice how f double prime of 0 equals to 0. So what do you notice? At x equals 0, am I guaranteed to have an inflection point? And the answer is no, because if you know the graph of x to the fourth, and remember, this second derivative is giving me information about x to the fourth. If I were to graph x to the fourth, doesn't it look something like this? And this guy is actually always concave upwards. It's never, ever concave downwards. So, and in fact, at 0, I don't have an inflection point. In fact, I have a local minimum. So remember, my potential inflection points will be where the second derivative is 0, but then I need to make sure that my second derivative changes signs, like it goes from positive to negative or negative to positive. So once again, it's very, very similar to how we find local maxes and mins. Remember, just because the first derivative is 0, we're not guaranteed to have a local max or min. We could say the same thing about the second derivative. Just because the second derivative is 0 at a number, we're not guaranteed to have an inflection point, but it's a potential inflection point. Okay, so let's move on to the second derivative test, and then we will do an example, and that will wrap up today's notes. So one thing I want to point out is a common mistake people make is, see, we learned yesterday that the first derivative test, that helps us find local maxes and mins. So a common mistake people make is they think that the second derivative test helps us find inflection points. And the answer to that is false. It's not. The second derivative test is also used to find local maxes and mins. So the second derivative test, the nice thing about it is it's a quicker way of finding my local maxes and mins compared to the first derivative test. However, the second derivative test does not always work. Okay, so the first derivative test, the good news is, no matter what happens, you'll always locate your local maxes and mins. The second derivative test, there will be instances where you won't be able to use this to find local maxes and mins, so you'll be kind of forced to use the first derivative test. So for me, I always prefer the first derivative test because everything's guaranteed to work. For the second derivative test, if it's a quick way or it's a shortcut of a quick way of checking something, you could use that. But remember, the second derivative test doesn't always work. So here's what the second derivative test says. So suppose f double prime is continuous near C. So here's what we could say. If f prime of C equals to 0 and f double prime of C is greater than 0, so let's see what happens here. If f prime of C is 0, what does that mean? I have a horizontal tangent. So I'm going to draw it off to the left here. So at this point, I have a horizontal tangent. And then what do I know? If f double prime of C is greater than 0, what does that mean in terms of concavity? If f double prime of C is greater than 0, that means the graph is concave upward, which means if at this point the derivative is 0, the first derivative is 0, and it's concave upward, then what do you notice happens there? At that point, I have a local minimum. So then f has a local minimum at C. All right, and then the second statement is if f prime of C equals to 0 and f double prime of C is less than 0, so once again, the slope is horizontal of the tangent, and at this point, if f double prime of C is less than 0, that means it's concave down, which then, what does that mean? I've just captured a local max. So then f has a local maximum at C. So what's the problem here? What's the third? When can this go wrong? Notice how in part A, f double prime has to be greater than 0, and part B, f double prime has to be less than 0. So what we could say is, let's make a note here. If f prime of C equals to 0 and f double prime of C equals to 0, this is inconclusive. So it's kind of this guy. So when your second derivative is 0, then the second derivative test fails. So then you're forced to use the first derivative test. Okay. So with that said, just once again, remember the first derivative test, second derivative test, the purpose is the same thing. Okay, it's to find local maxes and mins. The second derivative test is just a quicker way if it works out. Okay, so let's look at our first example and our only example for this set of notes. We're going to say discuss the curve y equals to x to the fourth minus 4x cubed with respect to concavity, points of inflection, and local max or minimum. And then once you do all this, sketch the curve. Okay, so the good news is, and see, here's the perfect example of, we graphed this in analysis, but it wasn't 100% accurate. See, we didn't even know anything about concavity when we graphed functions in analysis. So we might have graphed something where it was completely off. But in calculus, now we're going to use everything we've learned to get a graph that's 100% accurate to this. Okay, so that's kind of like what's going on here. So to find local maxes and mins, I'm going to use the second derivative test just so we kind of have experience with that. But you could also use the first derivative test to find your local maxes and mins. So using second derivative test, what do I need? I first need the zeros of the first derivative. So y prime will be 4x cubed minus 12x squared. So let me set this equal to 0, which means 4x cubed minus 12x squared equals to 0. And I could factor out a 4x squared, which leaves me with an x minus 3. And so what do I notice here? My zeros are x equals 0 and 3. So now what we could do is we could say, okay, once I do this, I need to find the second derivative. Okay, so remember, when the first derivative is 0, now I want to know, is the second derivative positive or negative at these values? Because once I know that, then I could tell you if that's a local max or a minimum for this function. So to find y double prime, that just becomes 12x squared minus 24x. So now let's check this out. So if I plug in 0 for y double prime, what do I get? I get 12, 0 squared minus 24 times 0, and I get 0. So what's the problem here? My second derivative ended up being 0. So this is inconclusive. So I can't say that I have a local max or a min at x equals 0. In fact, I don't know. It could be a local max, it could be a local min, or it could be neither. So I'm going to keep going, and I'm going to find intervals of concavity. And hopefully, if at x equals 0, I have an inflection point, because what do you notice? 0 makes my second derivative 0. So if I have an inflection point at 0, then it cannot be a local max or min. So once again, let me just repeat that. It's impossible for a point to be an inflection point and a local max or a min. Okay, so think about that for a minute. How could this point be a max and an inflection point? It's impossible. So I'll keep going. If at x equals 0 I don't have an inflection point, then I'll probably be forced to use the first derivative test, and then to find out, is this really a max or a minimum? But if it's an inflection point, then I don't need to worry about x equals 0 again. So what's y double prime of 3? If I plug in 3, I get 12 times 3 squared minus 24 times 3, which that is going to be 36. And that's greater than 0. And what do I know? My first derivative at 3 is 0. My second derivative is positive, which means it's concave upwards. So that means we have a minimum at x equals to 3. So what we know is that f of 3, which if you do the math, I'm going to actually leave that up to you. I'm just going to tell you what it is negative 27. So 3 comma negative 27 is a local minimum. Okay, now let's go into, so we found a local max, or local minimum in this case. So we found basically the local max or the minimum. Now we need to find the intervals of concavity and inflection point, and then after that we're going to put that to use. Okay, so let's actually do that. So to find intervals of concavity, I need to know if the second derivative is positive or negative. So here's what we have. Y double prime is equal to 12x squared minus 24x. So to be able to make a sign chart for this guy, I need to find its zeros. So 12x squared minus 24x equals to 0. I could factor out a 12x, which that will leave me with a what? X minus 2 equals to 0. And so my zeros are where? X equals 0 and 2. So remember, the intervals that I'm going to write this in has to match the intervals of the original function, which this is all real numbers. So my interval is going to be from where? From negative infinity to 0, and then from 0 to 2, and then 2 from 2 to infinity. So then what I need to know is 12x positive or negative? Is x minus 2 positive or negative? And then what I care about is their product, which y double prime is just this times this. And so whenever y double prime is positive, it's concave up. Whenever y double prime is negative, it's concave down. So from negative infinity to 0, 12x is negative. From negative infinity to 0, x minus 2 is negative. So negative times negative is positive. So what do I know? Y double prime, or my function y, is concave up from negative infinity to 0. So from 0 to 2, 12x is positive. From 0 to 2, x minus 2 is negative. So a positive times a negative gives me a negative, which is a concave down. So what did I just figure out? We have an inflection point at x equals to 0, which, what did I know? So remember how up here x equals 0, I didn't know if it was a local max or a min. Now that I know it's an inflection point, it can't be a max or a min. So I don't need to worry about using the first derivative test because I figured out what x equals 0 is, which in fact it's an inflection point. So, and in fact, if I were to plug in 0 in here, what do I get? I get 0 and y is 0. So at x equals 0, which the point itself is 0, 0. We have an inflection point. So what do I know? It's going to change from concave up to concave down. And then, so let's move on. From 2 to infinity, 12x is increasing, or it's positive. And then x minus 2 from 2 to infinity is positive. So a positive times positive is positive, which this is concave up. And what did I notice? I have another inflection point at x equals 2. And if you plug in 2 into the original function in here, you'll get negative 16. So I'm going to write that down here. So that's the point 2 comma negative 16. Okay, so now we're ready to graph this. So I have my intervals of concavity. I have my local max and my inflection points, and, or I'm sorry, the local min, not the local max. So then we're ready to graph this function. So this is going to be a sketch because of we have such large numbers. But what do I know? 0, 0 is an inflection point. And then what else do I know? 2, negative 16. So let's call this negative 16. Okay, this is another inflection point. And then at 3, negative 27, I have a local minimum. So what do I notice here? Let's go back to our intervals of concavity. From negative infinity to 0, my function is concave up. So concave up means it has to look like this. And so when I look at this, what do I notice? If I'm drawing something that's concave up, it has to do something like that. Okay? And then what do I notice? After 0, it changes to concave down. So it's going to change concavity. And then at 2, it's going to change back to concave up, and then we're going to hit a minimum, and then it's always going to be concave up. So if it's concave up, it has to turn around and go up like this. Okay, so notice how here's my sketch where I have concave up, concave down, concave up, and it's concave up all the way through. So here's actually a really good sketch of that function. With that said, in later sections, we're going to come up with more kind of steps to follow, because to get a more accurate graph of this, or to be more confident with us, it would be nice to know the intervals of increase and decrease and so on. But you could see just by using the ideas of concavity, local maxes and mins, inflection points, I was able to get a graph that's 100% accurate to the original function. Okay, so that takes care of the second derivative test and the intervals of concavity and so on. So that wraps up section 3.